We are given an array. We need to find out maximum sum of a subarray in this array. What is a subarray? Subarray means contiguous elements picked from the array. For example, if you have this array as input, the possible subarrays are 1, 2, 3, 1, 2, 2, 3 and 1, 2, 3. Please note that 1, 3 is not a subarray because 1 and 3 are not contiguous. Now, which of these subarrays has the maximum sum? This has sum 1, this has sum 2, this has sum 3, this has sum 3, this has sum 5 and this has sum 6. So our output is 6 for this subarray. Now, when you have all the positive elements, your output is always sum of all the elements. But when you have negative elements, the problem becomes tricky. Let's see some examples. In this array, the maximum subarray that we get is this one. We get the sum as 7 minus 1, 6 plus 5, 11. Now, if you consider any other subarray, you are not going to get the sum more than 11. For example, sum of this subarray is 5, right? And sum of this subarray is minus 8 plus 7 minus 1. So 11 is the maximum possible sum that we can get in this particular array. Let's see the second example. Here is an example where we have all positive elements. So our sum is 16. Let's see this example. This is an example where we have all negative elements. In this case, our output is largest value. Largest of all these three values is minus 1. So our output is minus 1. Now please pause this video and think of an approach that takes an array as an argument and returns maximum sum of a subarray in it. Let us talk about the naive solution first. In this naive solution, we simply traverse through all subarrays and for every subarray, we find the sum of it. And if current sum is greater than the maximum sum that we have found so far, we update the maximum sum. We store the maximum sum in a variable result. We initialize the result as array 0. Now we traverse through all the subarrays that begin with I. We run a loop for I equal to 0 to n minus 1. For every I, we traverse through all the subarrays that begin with I and find out their sums. So when we are at I equal to 0, we find out the sum of all subarrays that begin with I equal to 0. We find out sum of this subarray, then this subarray, then subarray with these 3 elements, then subarray with these 4 elements, and then subarray with these 5 elements. And whenever we find a sum, we compare it with the result. And if sum is greater than result, then we update the result. So we store the current sum in a variable called current, and we update the result when current is greater than result. Let's now see what happens. How does this work here? For I equal to 0, we are going to have initially current equal to 0. Then we are going to run a loop beginning from j equal to I. So when j is I, j is here, our current becomes 0 plus 1, 1, right? And when current is 1, we compare it with the result. It's not greater than the result, so we do not update the result. Now we move to the next element, j comes here, and our current becomes minus 1. At this point again, current is not greater than the result, so we do not update the result. Now we move to the next element and we get the current as minus 1 plus 3 equal to 2. And at this time, current is greater than result. So we update the result. Now we move to the next element. Our current becomes 1. We right now have current as 2. When we are coming here, we are adding minus 1 to the current and we have 1. Then we move to the next element. Our current becomes 3 and result becomes updated, right? Because this current is greater than current result. Similar things we do for I equal to 1, then for I equal to 2. When we come for I equal to 2, we find the sum more than result, right? We will find the sum as 3 minus 1, 2 plus 2, 4, which is more than current result. And at this point, we will update the result and this is the final value. And then we will return the result as 4. So this is how the solution works. The time complexity of the solution is big O of n square because it simply runs 2 loops. Now please pause this video and think of an approach that works in big O of n time. Let us now talk about the efficient solution. In this solution also, we traverse the array from left to right. And for every element, we find out maximum sum of a subarray that must end with this element. And our overall result is going to be maximum of all these values. Let's understand this solution with this example. For every element, I have written maximum sum of a subarray that must end with this element. For -5, it's -5 because there's only one choice. For 1, you have two choices. You can either take -5 plus 1 or you can take 1 only. Maximum of these two is 1. For -2, you have three choices. You either take -2 or you take -2 plus 1 or you take -2 plus 1 -5. Out of these, maximum is -1. For 3, you have four choices. You take only 3, you take 3 -2, you take 3 -2 1, you take 3 -2 1 and -5. Out of these, maximum is 3. Similarly, we compute maximum sum ending with these elements and ultimately we find out the maximum of all these values and return this as a result. Now the question arises, how can we do all these computations in big O of n time? Now please pause this video and think of a way to do these computations in big O of n time. To give you a hint, we are going to use maximum sum of subarray ending with the previous element to compute the maximum sum ending with the current element. If we take a closer look at this example and if we do some more examples, we can figure out maximum ending with index I can be computed as maximum of these two values. You take the maximum ending at index I minus 1 and add array I to it. That's one choice you make. The other choice is you simply consider only array I. The first choice is extending the previous maximum. The second choice is starting a new subarray with this element. So either extend the previous maximum or start a new subarray. Let's understand this with this example. When we are at -5, we do not have any previous maximum, so we have only one choice here, array I. So we have array, this maximum ending with -5 is -5. When we are at 1, we have two choices. We either consider -5 plus 1 or we consider 1 only. -5 plus 1 is -4 and only 1 is 1. So the maximum of these two is 1. When we are at -2, we have again two choices. We either consider 1 minus 2, which is -1, or we consider -2. So maximum of these two is -1. When we are at 3, we again have two choices. We take this -1, right, maximum ending with I minus 1 and add 3 to it. So we get 2. The other choice we have is 3. So the maximum of these two is 3. So we pick 3 as an answer. When we are at this index, we again have two choices. We take this and add -1 to it. What do we get? We get 3 minus 1, 2. Or we take -1. Out of these two, 2 and -1, which one is the maximum? 2 is the maximum, so we take 2. That's how we get the maximum ending with this element. So for every element, we are simply considering maximum ending with the previous element. When we are here, we have two choices. We take 2 plus 2, 4, or we take 2 only. The maximum of these two is 4. When we are here, we have two choices. We consider 4 minus 2, 2, or we take -2 only. Maximum is 2. So the idea is to either extend the previous subarray or start a new subarray. And how does this work? See, if you have to find out maximum ending with the current element, you will have to go through the previous element, and you already have the maximum ending with the previous element. So we reuse it. Now please pause this video and try to implement this approach yourself. You need to do it in big O of n time, and you need big O of 1 extra space. And you simply need to traverse the array from left to right. Let us now see implementation. In the implementation, we initialize our result as array 0. We initialize max ending also as array 0 because for the 0th element, max ending is always array 0 because there is nothing before it. From the second element to last element, we again find out max ending using one of these two choices. We extend the previous maximum or we start a new subarray. Whatever is giving the maximum is max ending with I. Right? So this is max ending I minus 1, previous value of max ending, and this is max ending I, current value of max ending. And after we find the current value of max ending, we check if it is greater than the current result. If it is greater than the current result, we update the result also. And at the end, we simply return the result. Let's now do a dry run of this approach. We have this array, and we have result as array 0, which is -3, max ending also as array 0, which is -3. we run a loop for I equal to 1 to 5 from here to here, and for every element we take these two choices. The current maximum ending is computed as previous maximum ending minus 3 plus 8 comma 8. Maximum of these two is 8, so we update the result as 8 because result is this max ending is greater than the current result, so we make the result as 8. For I equal to 2, we again have two choices. We either extend the previous max ending 8, we add minus 2 to it, or we start a new one minus 2. Maximum of these two is 6. This is not greater than result, so we do not update the result. For I equal to 3, we again have two choices. We either do 6 plus 4 or we do 4. We take the maximum of these two, we get 10, and this time maximum is more than result, so we update the result. Similar steps we follow for I equal to 4 and 5, and for I equal to 5, we get the maximum result as 11. And the subarray that has maximum sum is this subarray. This has maximum sum 11. So we got the maximum ending with this element, which was our overall maximum, and this algorithm returns this result at the end, 11. Now time complexity of algorithm is clearly big O of n because it's running a loop, and inside the loop it's doing constant work for every element.